Hello, I'm Michael Schachter, Product Marketing Manager at Allot. Welcome to the Mobile Virtual Conference. Our next session is with Ronen Priel, the CTO at Allot, and we're going to hear all about how machine learning and artificial intelligence are taking Allot smart and Allot secure solutions to the next level. Ronen?
Thank you, Michael. And in this presentation, I will present a few use cases of how Allot is employing machine learning technology in order to provide a solution both in the security and in the application identification and network management domains of its products. In general, I can say that since the general internet went dark, meaning the encryption became such a huge part of the traffic, or a big part of the traffic is now encrypted, the need to use sophisticated algorithms like machine learning algorithm is increasing all the time. In Allot and in general in the telecom industry, mainly because networks have gone dark, meaning that the percentage of encrypted traffic is increasing all the time, and today it depends on which analyst you are mentioning, but the estimations are varying between 50 to 80% of all network traffic is already encrypted. Now, since the data is encrypted, it makes it very hard to use legacy methods for application identification or DPI, and also for network security, since we do not see the actual traffic and the actual protocols and signaling that we used to see until somewhere between 3 to 8 years ago, depends on the application. So what I will try to show in this presentation are 4 examples of how we employ machine learning technology to overcome the issue of encryption and still get to reasonably accurate results which can enable our telco customers to conclude with either network management oriented or security oriented conclusions. So first, a quick reminder about machine learning, and I will focus specifically on the most popular type of machine learning, which is called supervised machine learning. In supervised machine learning methods, the concept is that instead of teaching the computer a very specific algorithm, which include very specific rules of how to react to what you might find in the data, supervised machine learning is different. The algorithm is saying, listen, don't teach me the rules, show me the data. I will learn the rules by myself. How will I learn them? Besides the data itself, also show me some kind of feedback or label over each of the data elements that you show me, and based on this conjunction between the data and the labels associated with it, I will learn by myself, the rules that will be used to classify or to analyze future data which was not part of the learning process. Now, if all this sounds complicated, let's look at the example that I'm showing right now on the screen, which is a simple one, and then I will show you real examples of how we do it. So what we see now on the screen, on the left side is the learning process, and on the right side is the production phase after the learning has finished. So in this specific case, we are showing an example, a very classic, by the way, example of supervised learning of image identification, meaning you see a lot of images. They can be of animals, and the goal of the algorithm or the model, usually when you deploy a machine algorithm model to a specific machine learning algorithm, to a specific problem or use case, you create a model. That's the terminology used in machine learning. So in this specific case, the model is trained to identify the image and to classify them into 2 options. Either they are cats or no cats. That's one of the most classic examples of machine learning in the world. So in the training phase, instead of teaching the algorithm very specific rules about what is a cat and how does it look and how to identify the ears or the face or the nose of a cat, instead, supervised machine learning is taking a different approach. The algorithm is saying, give me a lot of pictures. Let's say 2 million, 10 million pictures. Let's say half of them are cats and half of them are not cats. And for each of those images, tell me one thing, is it a cat or not a cat? And if you give me enough information, labeled information, I will create a model that with very good accuracy can get, after the training is finished, additional pictures of animals, and I will be able to tell you very accurately if this is a cat or not a cat for every picture. Meaning the model is learning by itself only by looking at data and the associate label or classification, cat or not cat. It learns how to do it accurately for future data which was not part of the training process. That's the core of what supervised machine learning is doing. So now let's look at real use case examples which are using the same concept of supervised machine learning into the world of Allot's products. And we'll start with 2 examples in the security domain and then move to 2 examples in the network management or application classification domain, what we used to call in the past DPI domain. So let's start with security. The first thing I'm showing is social media monitoring. As I'm sure you know, Allot is offering a very broad portfolio of security as a service package to telecommunication operators, which enables the telecommunication operators to offer such services to their consumer customers at home. So we have this in the package, we have legacy solutions like antivirus and anti-malware, anti-phishing, anti-bot and anti-ransomware, many issues which interest or should interest the consumer at home. One of our latest additions to this portfolio is the social media monitoring, or in a different name, anti-bullying monitoring solution. And the goal is very simple and it's very clear to everyone, especially to every parent in the world. You would like to know, and I would say that this solution is mainly aimed at parents who would like to monitor what is happening in the social network activity of their children. This is a very sensitive issue and is very important to every parent, at least that I met so far. So the solutions that we are offering is implementing exactly this. It also enables you to know where your children are and get alerts when they are moving outside of a specific area based on map definition over a map. It can also enable you to manage the time, the screen time of your user, how much can they use their mobile phone, where can they browse to, and so on. But the core of the product, and what I'm going to talk now, is the ability to look at social media messages, WhatsApp, Facebook, and any other social network, and to raise an alert to the parent whenever there is a message inside those social network which includes some kind of verbal violence. And you can see here examples, before I explain how we do it, you can see here examples of types of verbal violence. We can see here on the right 4 types of messages which include violence, and for each of them you can also see the severity according to our system of those messages. So for example, if you have a message which is talking about actually stealing something, like stealing the car keys, this is getting a red, very high severity. Also, if you talk about buying marijuana, like in the 3rd message, you get a high severity. And you can get a medium severity for cursing, like you're a fat fuck, you're fat and ugly. Those are, of course, very sensitive messages that you should get an alert on. However, we do try to distinguish between criminal and non-criminal activity, for example, as a differentiator for the severity of the message. So how do we do it? So the first part is actually to get the messages into our computer, into our algorithm, and this we are doing by deploying some kind of our code on the mobile handset of the children and taking some screenshots all the time of the social media application and running it through some OCR, which is our commercial off-the-shelf application for that. And in the end, what we get is that for every message that the kid either sent or received from the social media, we have it as a string of text as an input to our model. And the way we do it in this solution, we are using convolutional neural networks, which are very famous as the main machine learning algorithm used for picture classification. By the way, the example I showed in the beginning about identification of cats is usually the basic example you give in every academic course when you teach the students what is convolutional neural networks. But convolutional neural networks, or CNN as they're called for short, are being heavily used in the last 5 years, I would say, also to analyze text. It was found to be a very efficient machine learning algorithm also for analyzing text. And this is what we are doing here. We built a convolutional neural network where every word in the sentence is an input feature into the machine learning model. And you can see here on the screen the neural networks that we are building. And we provide as an input to this model thousands or tens of thousands of messages with their label, with their severity, which we manually label them. And we do this for every different language that we want to support. So if we have it for English, of course, that's our first model. We also have it for Hebrew, we also have it for Italian, we have it for German. We are now working on Japanese version of it, and so on and so on. So we have to retrain the model for every language again. And for every language, we need to provide few dozens of thousands of labeled examples. Once we did this, the model is trained, and now for every new message that we will enter it will provide a classification. The classification in our case is what is the severity of the message. If there was no violence at all, we expect to see severity 0. If we are talking about something criminal, we expect to see severity 5. If we see cursing or very offensive words, we expect to see severity between 3 and 4. This is usually what we are aiming for. And we got, in the languages which we already support, we are already at the level of more than 90% accuracy in our classification, meaning that if we get 10,000 new messages every day, we know to identify correctly 9,000 of them. And we are working all the time in order to improve this accuracy in order to reach the level of 95, and even if we will be able to get to 99%. And this is very helpful for parents. And by the way, the parents can control a bit what do they want to do with the messages on which we are not sure. Because the 1,000 which I mentioned, which we don't identify correctly, usually we know that we are not sure about their classification. We know that there is a potential that we are wrong in the classification of those 1,000. And every parent can choose what is the threshold in which he would like to get an alert when we are not certain or not. Most parents, by the way, choose to get an alert on every message on which we have a doubt. They prefer not to miss any violent message, and they are willing to pay the price of looking at several messages every week, which didn't actually include violence, although we wrongly identified them as including one. But every parent can play a bit with this configuration and configure the system according to what is more convenient to them. So this is one example. And by the way, once you have this information, it's very nice for the telco and also for some of the parents to get some statistics. So you can see here, this is an example from our system, one of our systems in Italy. You can actually see some statistics of according to the geographical area of Rome, in this case, which type of subjects of inappropriate language was used in each different neighborhood of Rome. It's very nice to see. So this is one example of machine learning usage that we have. I'm moving now to the second example, and in this example, this is an example which is aimed to locate usage of DNS infrastructure in order to create a very sophisticated communication channel between a malware which was injected to a target computer, between this malware and its command and control server. So just to make sure that we are all aligned on the basic terms here, every malware, which is a hacker is trying to penetrate a computer, it manages somehow to hack the computer and then usually deploys some kind of malware in the computer which stays in the computer. Now this malware can do many things. Most malwares are usually being used to collect information and send it to the hacker because the hacker wants to know something about what's going on in this computer or in the network to which organizational network, for example, in which this computer is operating. There are, of course, more malicious malwares. For example, ransomware is a type of malware which actually threatens to delete your computer. This is the classical ransomware use case. The important thing to remember about those malwares is that they are not standalone. Once they have been inserted into a computer, usually they have some kind of command and control server outside in the internet with which they communicate every day, every several days, in order first to send information back and second to get new orders from the command and control server. And one of the big challenges of hackers, or from the attacking side and for the cybersecurity industry from the defending side, the hacker wants to create a command and control channel which is as secret as possible because he knows that the defense part, the cybersecurity industry, is always trying to find those communication channels and close them and destroy them. So one popular and very smart way of creating a command and control channel which is hard to find is to use what is called domain generation algorithm, or DGA. So what is the idea? You can see it here on the screen. The idea is that once the malware has been injected into what we call here the already infected devices, the malware in the devices is running an algorithm, and the hacker in the command and control server are running the same algorithm, which takes the date, the current date, as an input, and create as an output a list of random strings. And you can see them here, like this h43i5 so on.com. And then out of this list, let's say every day they manufacture 20 such random strings. The hacker chooses one of them, randomly by the way, it doesn't really matter which one, and goes to DNS domain servers, there are many of these in the free market, and opens and buys this domain name, using this random string as the domain name, and actually creates a domain name which is now publicly available in the internet. So like you have www.ibm.com is a domain name which everyone knows. They create a new domain name called h43i5ibio55n.com. And every computer in the network, in the internet, can communicate with this domain name as long as it exists. Now the real smart thing is that they create this domain name, they operate it for something like 2 hours, and then shut it and never operate it again. So actually every day this hacker is creating for 1 or 2 hours a temporary domain name which exists only for today. Now remember that the malware in the infected computer is running the same algorithm, and it has the same list of 20 random string. It goes over them one by one until it finds the one which was actually being used to create the domain. And now they can communicate with this domain name, with the server behind this domain name, not for real DNS purposes, like real DNS server, but actually in order to communicate whatever they want. And actually what they're doing with it is to communicate the command and control traffic. Now why is this smart? Because this whole mechanism exists temporarily for 2 hours, and it's changing every day. And this makes it very hard for threat intelligence solutions to actually find this domain, because even if someone identified that this theoretical or fake DNS server is being used as a command and control channel, actually, until this is being identified and being spread through the threat intelligence infrastructure of the internet to all of the security players, it's not relevant anymore, because this domain name will never be used again. Tomorrow they will create a new random domain name. So this is a classical infrastructure actually for zero-day attacks. because you cannot really find it based on threat intelligence. However, you can try and find it based on the technical parameters of the solution, or in this specific case, the string that is being used, if you remember how I explained the algorithm, is random. Now, a random string is something that a computer can learn how to identify compared to a non-random string. And this is what we are doing in order to fight this solution. We are actually trying to train a machine learning model that will accurately distinguish between random strings used as domain name servers, which have very high potential to be actually a command and control of a malware, and legitimate real domain name servers, which are usually not random. Now, this is not black and white. If it was black and white, we didn't really need machine learning in order to separate them. And the examples that I'm giving here in the slides are strings which are very random. In the real world, hackers are much smarter than that, and they create string names which are only partially random. And this is why you need a sophisticated algorithm like machine learning in order to correctly distinguish between what is a real domain name server and a fake one which is being used as a command and control channel for malwares. So what do we do here? We are actually looking at a lot of domain names, which in the training we created 1.5 million samples of strings used as domain name servers. Some of them we created from open source DGA algorithms, which actually create random domain name. I mean, you can find the code to some of those hacking algorithms in the internet and use it. And the rest we used legitimate URLs that we know from our network secure repository and our classification lists. So we have two classes. We know how to label every string in the training as, is it DGA, is it used for malware communication channel, or is it legitimate? So we have a training set in the size of 1 million. From each of those 1 million, we extracted several text features, like what is the length of the string, what is the entropy, which is a bit of a symbol of the level of order inside the string, what is the frequency of every character. For example, think for example in English on the frequency of vowel letters, A, E, I, O, and U. When you have, as much as the string is more random, you will see the frequency of those letters as any other letter. But we know that in real strings, in real English, those characters, those 5 characters, are much more frequent than any other character, and so on. So you can use this information to distinguish between random and non-random strings, and you can do the same for what we call the Charles bigrams frequency, which is the same concept, but you look at sequence of 2 characters and measures the frequency of every characters following another one. So you have a matrix of, in English, 26 multiplied by 26, and again, the frequency table, which you can see on the right, in random strings will be completely different than the frequency table of real English sentences. And so on and so on, and we can extract more text-related features. I only mentioned a few. And we use those features over those 1.5 million sentences in order to train the model. And then we test the model over additional almost 400 sentences which were not part of the training. And you can see here the performance of the model. So out of these almost 400,000 sentences, you can see that the model identified correctly almost all of them, everything which is in a green background. So out of the 200,000 almost which were used for malware communication channels, the model identified above 99% of them. And the same goes for real URLs or non-fake ones which were used as a real domain server. And this is an example of a machine learning algorithm which achieved extremely high accuracy, which means that the problem in this case was simple enough for this model. Now I'm showing here the accuracy of the model on 100% random strings. In the real world, as I said before, some of the strings and some of the hacking algorithms are much more sophisticated, and the strings that they produce are still random, but less random than what I'm showing here. And then the accuracy is a bit less, but still, machine learning algorithms prove to be extremely efficient in this type of classification between fake domain name servers and real domain name servers. And this is part of our network secure offering starting, if I remember correctly, end of H1 2020, or somewhere around this timetable. So this was the second example about security, and now I will move to two examples coming more from the from the domain of network management and application identification. So the first example in this domain is what we call cellular congestion detection, and I would like to explain what is the problem. Cellular operators are heavily concerned about efficient utilization of the radio access network. As anyone in the telecom industry is aware, 80% or around 80% of the total costs that a mobile operator is spending on building its network, including the BSS, I mean starting from the antennas to the billing and CRM, 80% of all of those costs, which are of course billions per network, 80% is for the radio access network. Meaning the channels, the frequencies that you must buy, the antennas, all of this equipment all over the country that you need in the areas in which you cover, all of the routing equipment to send the information to the core of the network and so on. So this is the biggest expenditure of the mobile operator, and they would like it to be as efficient as possible, because anytime they get to the limit of the capability of this radio access network, they need to expand the network, which is a heavy capital expenditure. So the goal that we have is trying to help the mobile operator to identify in real time which cells of the network are currently under congestion, which theoretically hurts the quality of experience of the subscribers in this cell, in order for us to immediately take actions to solve or to reduce the congestion in this cell. So once we identify that a cell is being congested, we know how to help the operator reduce the congestion. We do it by classical traffic shaping of prioritizing more critical application and deprioritizing less critical application and so on. And this part is the, let's call it, more straightforward one, and it doesn't include machine learning algorithm. The part that I would like to focus on, which we solved with machine learning, is how do you identify that a cell is being congested? But the challenge that we have in Allot is bigger. We do not sit and we do not see in real time information from the RAN, from the radio access network. Allot is located in the core of the network, and the challenge that our customers are asking us, can you identify in an accurate manner, only by looking at the traffic when it's going through the core of the network, can you identify that one of the cells or several of the cells are now being congested? And this is a solution that this is a challenge that we are solving with machine learning. So let me give a bit more details of how we do it. So first of all, what do we see when we sit in the core of the network and we take it from our Allot Smart platform? We mainly see technical information like our per session for every session. First of all, for every session, we know from which cell in the network it is originating from. So we know to correlate between every session and the cell in the network. And for every session, we can see the RTT information, the amount of traffic going in the session, the amount of new connections, some information about the TCP segmentation in every session, and so on and so on. There are many network TCP/IP level mainly information that we know for every session. So we are hoping to use this information in order to predict whether a cell is congested or not. So the first thing we need to understand also for the training phase is what does it mean congested? And the definition that I'm showing here is a definition that one of our customers made, and this is what we use in the specific case of this customer, is they're looking at the PRB utilization information from the run and saying if the PRB utilization in the cell, I mean the amount of frequencies being used right now, is more than 90% of the total frequencies of the cell, this is called the congestion. If it is less than 90%, it is not called the congestion. So this is the definition or the label that we used in this case. And for the training part, we got real labeling from the run, from the system, from the run software and hardware, and we use this to train the model. So what we got are 3 months of data of train set and 2 weeks of data of test set. And for every session in this period, we got the label from the run, whether there was a congestion or not at that time, again, based on the PRB utilization percentage. And we correlated this in the training stage with the information from Allot Smart, like the RTT, volume, TCP segments, and so on and so on. And you can see the amount of data we had. We had 1.7 million data points for training and 300,000 data points for testing. And first of all, I will show you the bottom line. We got to a level where, looking at 44 cells, which is the information that we showed before, we get to 95% accuracy, but even not less important, the amount of false positive that we have is relatively low at 4.4%. And by the way, we hope that we can improve it over time when we evolve the model to be smarter. So those are very good results, which took us a lot of time to get to it, but we are now in a level where per network, assuming that we do some relatively straightforward retraining over the models that we already have, and some fine-tuning to the specific network, we can get to a relatively good accuracy of, let's say, over 90% of knowing for every, in real time, by sitting and looking only the traffic at the core of the network, for each of the cells, is it now being congested or not, assuming the congestion is, as we defined before, the percentage or some threshold of percentage of the PRB utilization in the cell. And I will show, just as an example of how the algorithm, try to explain a bit how the algorithm works and why is it important to have many features. You can see here an example of 10 features. 10 features, I mean information that we can get for every session while sitting in the core. So you can see here the information. I mentioned already a few of it. And you can see in the graph, you can see that the y axis is the PRB utilization, and not surprisingly, everything which is above 90% in the y-axis is marked as yellow. This is congested. Everything below is not congested. And what I'm trying to show here is how adding more and more features helps us to get to a right classification. So if I'm just looking at one feature, in this case it's the RTT, one feature means I can pass one line over the graph and try to somehow split the information, and you can see that we will have quite a lot of false negative and false positive if you're using only one feature as the basis for classification. Now if you use two features, in this case RTT and volume, you can see that we can get already, now we can pass two lines in order to classify, and you can see that we are getting already to better results, meaning the amount of false positive and false negatives that we have, data points, is smaller. And if we add more and more features, we gradually decrease the amount of false positive and false negative. And in the next slides, I'm trying to show you once we get to 10 features, and I'm using some trick of showing you in 3D something which is actually 3-dimension. I'm trying to show you information which is actually coming from 10-dimensional space, because we're talking about 10 features, but we have some tricks in machine learning of how to visualize it. So you can see when we get to 10 dimension, we can already separate quite well, almost without false positive and false negative, between the yellow data points, which are the congested cells, and the non-yellow ones, which are the non-congested cells. And you can see that when you add more and more features, the separation, hopefully, becomes better and the amount of mistakes becomes smaller. And this is what it means to have a good machine learning model. It's a model which results in very small amount of mistakes and predict correctly most of the data points. And in this specific case, we managed to do it. I want to make it clear that there are problems which are very tough to solve also with machine learning, and even if you add a lot of feature, you never get to a very good separatable space or space in n dimensions. But in many problems, like in this one, you can actually get to very good points, and we can actually visualize it very nicely with this picture. Now, the last example I will show, which is again in the application identification domain, is a very common request that we got from many customers in the last few years, which is YouTube started a few years ago to offer a new service besides the classical, YouTube streaming, which we are all using. There is a new, relatively new service of live video streaming from subscriber to subscriber, so from subscriber to a group of subscribers. And many of our customers would like us, as a classical DPI application identification challenge, to distinguish between those two. Now, from technical protocol point of view of YouTube, they look the same. So it's very hard to predict, to differentiate, and the only way, at least that we managed to do it, is by using machine learning traffic. And you can see here some of the, and again, the concept is similar to what I showed before. We collected thousands of regular YouTube movies and thousands of live streaming YouTube movies from the new service. So we knew the label in the training phase, and we trained a machine learning algorithm to create a model which is focusing on this problem. And then we gave this model new videos which were not part of the training process and tested to see how good the model is performing. And you can see that in this case it's very different. It depends also on the platform, meaning mainly the operating system in which YouTube is used. So Android and iPhone and Windows are not necessarily the same. Also, by the way, between different manufacturers of handsets which are all using Android, you can get different answers. So there are a lot of complexity here in order to solve this challenge, because we need to test our model on many combinations of handset and operating system and version of operating system. So there are actually many different scenarios, and for each of them we need to test the accuracy of the model. And you can see here that in some of the cases we get to a very high numbers of 85 or 92 true positive, correct results. And in some cases we get to low, but in some cases we get to high false positive results. So the results are different according to the platform, but still in many cases we do get to very good results. And this is an algorithm that we are, by the way, still working to improve the results by trying to bring more data, more features, and in some cases also trying new machine learning algorithms which might perform better than the algorithms that we used so far. So that's it. I showed here 4 examples of using machine learning in real use case, in real world, of products of Allot which are being offered as part of the Allot portfolio. And I would summarize by saying that we believe that that machine learning technology is critical for the continuation of our offering, and in general I believe that it will continue to and only continue to grow and be even more important part of network management, network monitoring, as well as security solutions, not only in Allot but all over the industry. And we are increasing the amount of investment, budgets and headcounts that Allot is investing in this domain, because we believe this is one of the keys to maintain our technological leadership in the markets in which we are operating. That's it. I hope you enjoyed, and I hope that you will find interest in this domain as I do, because really I think this is a very fascinating technology domain in our industry. Thank you very much.
Thank you, Ronen, and thank you all for joining us. This is powerful stuff. Please feel free to tour about the mobile virtual conference area. And for questions or getting in touch with some of our experts, please use the form that you'll see shortly, and don't hesitate to ask questions and to visit all of the features of the virtual conference. Thank you again, and thank you, Ronen.
Thank you. Thank you very much.